So, hi everyone. As I've just said, my name is Dan Scott, Director of Analytics at Arcadis Gen. So what we do at Arcadis Gen is we really specialise in using data and analytics to drive better decision making in our customer organisations. Typically, they are physical asset owning organisations at various different scales. And what they're looking for us to support them with is to with products and services is really about making better decisions around those assets to deliver better outcomes. So what I wanted to talk about today in this masterclass was really about the kind of the nuts and bolts of that, really, in terms of the use of optimization algorithms to support that process. So in terms of what I'm going to cover, we're going to have a very quick talk about what represents an optimal decision. And then shortly after that, we're going to play a bit of a game. So I'm going to invite you to join an online game, and we're going to explore kind of how human beings solve problems versus how algorithms solve problems. We're then going to get into the nuts and bolts of how various different types of algorithm work in the background, and we're going to explore aspects such as optimization under uncertainty and other kind of key variables, and then kind of bring that back and talk about what that means from a kind of industrial context. So first of all, then, so what represents an optimal decision? So optimization and optimality is a bit of an overused term to some extent. Quite often these days, it seems to get used more, to refer to making things better rather than making things best. When I talk about optimization in this context, what I'm talking about here is the use of some sort of algorithm to maximize or minimize some utility function. So where that utility function represents some value, where there is, we're looking for the absolute best possible outcome that can be mathematically achieved given a set of real world constraints. So yeah, that's really what we're going to be exploring as part of this. So the first thing we're going to do is we're going to play a bit of a game. So and what we want to do here is, because as human beings, we kind of think of ourselves as being actually fairly good decision makers in the most part, with the exception of that thing that you did at university that you now regret. We tend to think that in a non-emotional setting that we tend to be fairly rational actors. We tend to, if we've got all of the information in front of us, be able to make good decisions. So what we're going to do here is we're going to really put that to the test. And we're going to put it to the test by robbing a jewelry store. So in a second, we're going to send out a link on the chat, and I'm going to ask you to follow that link, and that's going to take you into the game. In the game, what I'm going to ask you to do is you're going to put in a nickname, try and keep it clean because it will be visible later on, and you're going to go into the game, and you're going to see a screen like we've got up at the moment, and we can see a whole load of jewelry on the left-hand side, and you can steal that jewelry by dragging and dropping it onto your swag sack on the right-hand side. The key issue here is a bit of poor decision making on the run-up to undertaking this robbery. Your bag that you've got can only hold 50 kilograms worth of swag. So if you put more than 50 kilograms worth of swag in it and try to leave, the bottom's going to rip out of the bag, and you're going to lose everything in that bag and score a 0. So the goal here is to try and get the maximum score in terms of the value of the things that you steal into that bag while not exceeding the 50 kilogram limit of the bag. You have tripped the burglar alarm on the way in, so you will have exactly 2 minutes to play the game before the police arrive, and you have to leave anyway. So I'll ask you now if the link can go out and people can start to kind of follow that link and start playing the game, and we'll give you kind of 2 minutes to kind of work through that game, do the best you can, score the best you can in terms of the items that you select. While you're playing that, so some of you might recognize this as being a fairly simple formulation of the knapsack problem, which is quite a famous and common kind of problem in data science, and it's really about optimum packing. So what we're trying to do here is we're trying to grab as many items as we can, pack those into the bag within a defined constraint, which in this case is the total weight of the items that you're putting in. So what we're going to do, I'm going to jump to the dashboard now, so that we can kind of start to see your results as they roll in. So hopefully you're all managing to kind of interact with the app now. You're making your choices as to which items to select. So I will caveat this to say that we only finished this app last night, so I've got my fingers crossed that it's actually working and we are actually capturing some data. There's nothing like testing your app for the first time in it with a large audience.
Just a super quick one, Dan. I can see you've perhaps getting some information through, but I think for a few people it's dropping them out. So I'm not sure whether you'll get a complete data set, but I just thought I'd give you a heads up in case that affects you, your further chat and stuff like that.
Okay, fine. Well, I'll give it another couple of minutes. Hopefully, some people are managing to some more people are managing to put their data into that. Okay, I'm gonna pause it there. I think sounds like we're having some trouble with the app, so not everybody's managing to get into it. So I apologise for that. We'll try and make the game available afterwards. So if you want to try your hand, then you can. So what I'm going to do, in the interest of moving on, I'm going to freeze the results there, and we're going to kind of have a quick look at the ones that have been selected so far. So in terms of the items that have been chosen, well, that's actually quite a dichotomy there. So we can kind of see that these 6 items here seem to be the most commonly chosen items, and there's some logic to that. We've got some high value items in here. Some of those also have some quite high weights and other bits and pieces. We can kind of look at that in terms of the item weight versus the item value, which you'll hopefully intuitively kind of realize is obviously quite important to this problem. So we can kind of see, this was the scatter of all the items in that list of 30 that we had within the app. So we can kind of see, there's an interesting scatter. We can see that there's some items here that have a relatively high value with a relatively low weight. So we kind of expect these to be quite valuable in this exercise. And we've got some that have quite a high weight and a low value, which conversely we expect to be of little interest. We can have a look at in terms of which items were most popular, and again, a lot of this kind of looks to align with what you'd expect, although these are a little bit less selected than maybe I'd expect. But we've got some kind of items up here which seem to be slightly above the kind of average line that people are selecting. So now what we're going to do is we're going to go back and we're going to run first of all a prioritization algorithm on this to see what sort of answer. So we can see that kind of the best score we've got in here so far is 99 pounds in terms of the value. So if we run a prioritizer on it, runs nice and quickly, and we can see a prioritization algorithm is able to find a solution in here that scores 115. So that's quite a considerable uplift in terms of the score. And if we go and have a look at which items it's selecting, there's some real logic to that. So again, these 3 here, these kind of high value, low weight kind of items just here, as well as these items kind of on this axis here. Those make some sense. We've got this one down here, which is interesting, and we'll have a look a little bit more of a look at that later on as to why that gets selected. The next thing we want to do is say, okay, well, there are the other types of algorithms. So the next thing we're going to run is a linear optimizer on this problem. So let's run that linear optimizer, and we can see the linear optimizer is able to beat the score again. So it's able to get to 118 while still only kind of packing to 50 kilograms. So if we have a look at what this selected, we can see that what it's selected is a slightly different mix of items. So again, it's gone for these items here, which are fairly obvious. It's not gone for the one down here. This one, which was quite popular, it's left that. And up here, this is quite interesting because on paper you'd kind of expect this to be more valuable in that it's slightly further up the value kind of weight ratio than these 2, but for some reason the optimizer has chosen not to select those. So again, we'll explore that in a little bit more detail. But the key point here is that, within this problem, and that's, this was a relatively simplistic problem in terms of having kind of 30 items within the jewelry store that we were interested in. We had only one constraint, which was the weight constraint on the bag, and yet the sort of scores that we're able to get are actually quite poor relative to what is actually the optimum answer. And so let's have a bit of an explore as to why that is. So a lot of you might kind of say, well, actually, part of that is because you didn't give us very much time to solve that problem, and therefore, if we'd had longer with the information that was on the screen, we could have worked out a better list of things that we could put into the bag, and that's certainly true. And if we'd given you a bit longer, a bit more time to explore, a bit more time to experiment with putting stuff in and out, and those sorts of things, that's certainly true that you'd have been able to improve your score. But would you have been able to get to the best score? Ultimately, if you're going to solve the problem by trial and error, you're going to have to work your way through all the different combinations of how to pack things into that bag in order to kind of check each one and see which one actually gives you the best total value of stuff to steal. So let's have a look at what that would imply. So on the screen at the moment, we've got two plots. So the left-hand plot is showing us a plot of, depending on the number of items that we're choosing to consider, how many combinations of ways of packing the bag exist. And the graph on the right is showing us, given how many combinations we'd have to calculate, what would be the time it would take the current world's fastest computer to undertake that calculation. And here we're being quite generous, and we're assuming that each calculation is only one clock event on that particular machine, and therefore that's probably a massive exaggeration in terms of how quickly it could do it. But if we start with kind of just two items, so if we had a particularly empty jewelry shop, only has two items to choose from. As you can imagine, but when I'm packing that sack, I've got four options. So I've got an option of selecting neither. I've got an option of selecting the first item, an option of selecting the second item, and an option of selecting both items. And I need to kind of assess whether any of those breach my weight limit for my bag, and I want to quantify how much value that is. So I've effectively got to quantify four different combinations in order to assess which one is the best. By the time we get to four jewelry items, I'm now going to have to assess 16 different combinations of items that and calculate their relative value. By the time I get to 10 jewelry items, I've now got to assess over 1,000 different combinations and try and look at which one's the best. And we had 30 items in our jewelry shop, so by the time we get to 30, we'd be at well over 1 billion combinations. But obviously, 30 items in a jewelry shop is still a very, very small number for that problem. So let's actually have a look at this a little bit further. So if we had 40 projects to assess, we're getting to the point where the numbers are getting so large that, first of all, we've kind of breached through the maximum number of cells allowed in an Excel spreadsheet. So certainly, the humble spreadsheet is not going to be sufficient to solve this particular problem. And we've also breached through the limit that represents, we've got more combinations now than there are stars in the Milky Way. Our fastest computer is still chugging along quite nicely. It's still doing that quite fast, so that's good. By the time we get to 70 different items in our jewelry store, we've now exceeded the number of combinations we've got has now exceeded the number of stars in the entire universe. And we can see in terms of our computation time that actually now we're getting into the thousands of seconds. So we're starting to see some very significant computation times starting to creep in now in terms of 70 different jewelry items to select to go into a 50-kilogram limit bag. If we take this a little bit further, by 120 different jewelry items, we're now, the amount of time that the world's current fastest computer would take to solve the problem has now exceeded the amount of time between now and when the sun is expected to expand and consume the Earth. So at some point, if we want to carry on this calculation, we are going to have to move our computer to somewhere outside of the solar system. By 270 projects, we have, combination-wise, we've now exceeded the number of atoms in the universe, which obviously, is now starting to get to be very significant numbers now. And by 400 jewelry items, our computer's now taken so long to calculate the total number that we've exceeded the amount of time predicted until the heat death of the universe, at which point we've probably taken this metaphor about as far as it's worth going. Now, it's worth noting that for for a typical kind of business application, business decisions, we're not just talking about 400 different things to choose from. We could be talking about thousands of different decisions that we know, or many thousands of different decisions, and we might need to make those decisions, over different days, different months, different years. So we could end up with tens, hundreds of thousands of different things that we're trying to choose from. So what we're looking at here is the problem around kind of solving these problems with brute force. You're not going to be able to search through enough combinations to actually find the best answer just by kind of manually looking and trying things out. Okay, so we're going to start to now look at other ways of solving this problem. So there are various different optimization techniques available. So the most simple end of the spectrum, we've got kind of Boolean logic. So this is just if-then rules, the most kind of basic things, rules of thumb essentially, that we can define that kind of give us some guidance as to what sorts of decisions to make and when. Those will be the kind of lowest kind of quality in terms of their ability to find the best answer. They're actually very unlikely to find the best answer. The next up in the kind of hierarchies, we've got prioritization algorithms. I'm going to go into those in a little bit, just next. But you kind of saw on the dashboard before that we ran the prioritization algorithm. It did a good job. It beat all of the scores that we had, but it wasn't as good as the optimization engine. Next, we go to linear optimization. Again, we're going to explore this in a little bit more detail, but this allows us to solve independent problems that are linear in nature and find the best possible solution. And that's what we saw again in that dashboard that was able to score that 118. And then finally, we have nonlinear optimization, which is where we get to the really thorny kind of hard problems where we have multiple kind of links between the decisions that we make and impacts and other bits and pieces that we need to solve. And therefore, we're searching a very, very complex decision space for the best possible solution. And again, we'll have a bit of a look at those. Okay, so let's start with prioritization then. So on the screen now, we've got the 30 items that were in our jewelry store. And I've added an additional column here, which is to include the kind of value per kilogram of each item, because instinctively we kind of understand that the kind of value density of the items is likely to be important to this. So what we can take is that column, and if we sort it in descending order, we can kind of see that actually at the top of the list we've got a couple of items here that have very, very high value value densities. Clearly those are going to be very good things to put into our bag. And as we work our way down the list, clearly they are lower and lower density, and therefore we're getting less and less value for each kilogram we're putting into our bag. So from a prioritization perspective, we've got this limit of 50 kilograms. So the logical thing to do is to work our way down the list and kind of fill up our bag with the highest density items. So we can do that very simply. We can add the cumulative weights, and then we can work our way down. So working from the top, I mean, I can get kind of 6 items, into my bag, and I'm up to 44 kilograms. So I've now got 6 kilograms worth of space to fill. And what I can do is I carry on working down my table, looking for the next item I can find that is 6 or less kilograms. I find it down here with this sapphire brooch. And that gives me my 115 pounds worth of items and a total weight of 50 kilograms. And in principle, this feels right. And it plays into a kind of fault in our kind of human decision-making process. This feels logical because we are working our way down, in order of priority. All of these items in the middle here, this gap, the reason we haven't selected them is purely because they don't fit. So we kind of feel like we've kind of loaded up our bag with the most valuable things that we can fit within the constraint. But let's have a look at that compared to what the linear optimizer chooses. So the linear optimizer chooses obviously a different set of things. And the reason it does that is it's missing, it drops out these 2 middle items here, which on paper look very, very valuable. But they are actually quite high weight. And by dropping those, it's able to get these 3 in. And this is the underlying kind of principle of this, is the critical thing is not the value density of each individual item, but the average value density of all of the items. So by kind of not putting this low density item in and being able to shoehorn one more higher density item in, it can afford to offset the loss of not including these 2 and exceed that offset to actually deliver a better overall outcome. And what this kind of leads us to is the sort of general case that prioritizers will very rarely provide you with the optimum answer. They will only do that in a very special case, and that special case is where it just happens to be that when I rank my my items in priority order, they at some point in the table it exactly adds up to the constraint without any breaks in it. And in that special case, then the optimizer and the prioritizer would agree as to the correct answer. But in all other cases, the prioritizer will find a good answer. It just won't find the best answer. So if we have a look at the kind of the relative pros and cons of using prioritizers. Now, one big pro of a prioritizer is they are easy and intuitive to understand. They play to our natural kind of inbuilt instincts as to how things should work, even though they don't. So actually, when we're explaining those, and particularly from an Arcadis Gen perspective, since most of our customers are engineers and other people who aren't necessarily completely au fait with data science and the techniques that we're using, if being able to explain it in a very, very easy to explain, straightforward to understand way actually has certain advantages. They are computationally efficient because all I've got to do is rank my items and draw a line at a certain point down. But the big drawbacks are they'll only find that actual best solution under specific circumstances. So if it is actually important to find the best answer, and where there are some significant financial savings or performance savings or anything else to be found by finding that marginal gain, then the prioritizers just aren't really good enough. And they also struggle to deal with multiple constraints. And unfortunately, those are quite typical in the real world. It's very rare that we're only constrained on one front. In this case, we're only constrained by the weight limit of the bag. But in reality, we might have been also constrained by the size of the bag, the total volume of it. If I can't physically get it out of the door because it's so big, that might be a problem as well. So I might be constrained on multiple fronts. And indeed, in the real world, generally speaking, it's not just budget constraints, but also resource constraints and access constraints and various other kind of targets that we need to meet. And prioritization algorithms really struggle to deal with kind of multiple constrained problems. Okay, so let's have a look at linear optimization then. So the first thing we need to kind of introduce with the concept of linear optimization is the idea of bounds and goals. So a bound is some constraint or set of constraints that I absolutely cannot exceed. So obviously in the knapsack game, it was very much around that 50 kilogram limit process. The goal is the utility function. It's the thing I'm trying to maximize or minimize, from the algorithm's perspective. So what I'm asking the algorithm to do is look at generally the sum of that particular value across everything I've selected and find me the best possible way of doing it. And the way it works, so I'm going to look at a very, very simple example here. So it would have loved to have been able to kind of show you, relative to the knapsack game example, but because we've got 30 different decisions to make in the knapsack game in terms of 30 items, that would be a 30-dimensional problem. And I don't know about you, but I struggle to mentally picture 30-dimensional objects. So what I've done here is presented it as a very simple problem. We've got two decisions, a decision around X and a decision around Y. And our decision is, what value to set it, and I can set it to any value. I've got two constraints. So in this case, I've got one constraint, which is that X, must be less than or equal to 8. And I've got a second constraint, which is, some linear progression based on X and Y that I want it to be less than. So that effectively describes a region of acceptable answers. So these represent my bounds, and this is the area that I want to search. My utility function, in this case, is a progression of X and Y, but again, in our knapsack game was very much about the value. So we can kind of see that plotted on here for simplicity. So we can kind of see as X and Y get larger, then the utility function also gets larger. The way that a linear optimization algorithm works, and I'm going to keep this fairly simple around a kind of simplex method type approach, but and not bring in kind of integer programming and other kind of key elements. But in essence, the algorithm will initialize at some point within the accepted zone. So it doesn't know where the peak is. It's just going to start somewhere within that zone. And the first thing it does is it looks around in its immediate vicinity in terms of that utility function, and is looking to see which direction to go in that leads it uphill the fastest, in essence. It identifies that, and then having kind of worked out the direction, effectively solves the linear equation until it reaches one of the bounds that have been defined. In this case, this top line here, and it will move to that point. So at this point, it cannot move any further along that vector because it will breach the bound and it knows it can't do that. So at this point, it then starts to look around again and says, okay, is there any other direction I can move in that still takes me uphill? And the answer here is yes, we can carry on moving along this line, and that would take me uphill in the steepest way. So it'll follow that line and solve that linear equation until it hits the next bound up in this corner here. At this point, again, it cannot go any further on that vector because it would breach a constraint. Now, at this point, it's going to have to look around itself again and say, is there any other direction that I can move in that would still take me uphill? And the answer in this case is no. So now the algorithm would terminate having found the optimized result, which is up in this corner here. And generally, with linear problems, if it's a constrained problem, very often, more often than not, the optimized solution will exist in one of the corners between two or more constraints. So that's effectively what the algorithm is looking for. Now, the key word in linear optimization is, of course, linear. So if we look at this particular example here, we can kind of see that as x increases and as y increases, my utility function increases as well. In fact, if I took those bounds off, the answer would be the optimum answer would be for x and y to both be infinite, because that would be the obvious way to maximize my utility. That's obviously a very, very specific case, where those items are that utility function would always kind of rise with some linear function. So what happens when that's not true? What happens when my utility function isn't linear? And this may happen more often than you think. So if we look at the case of our knapsack problem, within the jewelry store we had earrings, and when you stole the earrings, you were stealing a pair of earrings. But what if we had those earrings in individually? Now, unless your market for selling your stolen merchandise includes pirates, earrings on their own, single earrings, aren't worth as much as a pair of earrings. So actually, in that situation, having just one earring or having the other earring, the sum of the two values of those might be less than having both earrings together. So now I've kind of introduced a connection between my decisions for earring 1 and earring 2 that result in a very different level of utility in terms of the value. And so that's starting to introduce kind of bumps and peaks and other bits and pieces into that utility function that makes it non-linear. So in the case that we've got on the screen here, now the algorithm really just doesn't know which direction to go in, because in essence you can go uphill in every direction. So it starts to just break down. Now, there are more advanced linear algorithms out there that do a slightly better fist of these sorts of problems and that sort of thing. But ultimately, what we're looking at here is a fundamental limit to the what linear optimization algorithms can do in terms of these kind of highly non-linear search spaces that it's got to go through. There are various techniques that you can bring to bear on this in terms of trying to represent your problem as linear as possible, but it really is incumbent on the data scientist that's using the algorithms to really have a feel for the problem that you're trying to solve. Is it a linear problem? Are your decisions independent of each other? If they're not, can you represent them to the algorithm in a way that they are independent? And if you can't, then you're going to have to start to consider non-linear approaches to the problem. So pros and cons of linear optimization. So they are still relatively quick to optimize, and that's a real big advantage to them. They are fast, and if the problem is linear, then they are pretty much guaranteed to always find you the best possible answer to that problem. And they are really, really good at dealing with multiple simultaneous constraints. I could put 1,000 different constraints on that problem, and it would still find me the best possible answer, and that makes them very, very powerful from that perspective. On the downside, though, if the problem is not represented as a linear problem, they are likely to come unstuck. They will either give you a suboptimal answer, or they will just give up and go home. And unfortunately, for us, many real-world problems are in fact non-linear. So again, unless you can find a clever way of offering those up to the algorithm, then that it can take linear optimization off the table as an option. Okay, so that. When you are stuck with a problem that is intrinsically non-linear, it's time to bring out the big guns. So we're going to have a look at non-linear optimization now, specifically genetic algorithms. So we're going to kind of explore, in principle how they work, and what they can do, and those sorts of things. So genetic algorithm, it's a class of evolutionary algorithm. There are other types of nonlinear algorithms, of course, but I'm just going to focus just on here. So in order to kind of bring this to life a little bit, I'm going to borrow some really good work from Raphael Matsunaga, and he built this this genetic cars web page to kind of really bring to life the idea of a genetic algorithm. So let's have a quick look at that. So what this is doing is it's generating a population of vehicles, and the key things about these vehicles are the kind of the shapes of the body, the diameter of the wheels and where they're fixed onto the body, also the kind of weight and kind of friction factor of these wheels. And they're trying to get as far along this track as they possibly can. And what we can see is most of the cars, in this case, completely fail at the first fence. Some of them get a little bit further, and that's the thing. But what's happening in between each race is that those those kind of characteristics are being kind of interbred between those things. So using kind of evolutionary techniques, it's trying to kind of bring through kind of survival of the fittest of the designs and key aspects of cars through. So that they actually get better and better at getting further and further down this particular track. I'm going to up this just a little bit, so we've got more of the survivors in each race. But what we can kind of see is that there's a whole list that gets generated. You have 20 different vehicles each time. Some of them are completely rubbish, as we can see, but this one's generally doing quite well. And over time, we kind of expect to see more and more, of the attributes of this being inherited by the children of this particular vehicle, because it's going to be more likely to breed more offspring. So now we're starting to see more and more vehicles looking a little bit more sensible. What I'm going to do is I'm going to leave that running in the background, and we'll come back to it in a little bit and see how we're only up to the 4th generation. We'll come back to it and see how it's faring. Okay, so let's have a look at a little bit in depth about what's going on behind the scenes there. So a genetic algorithm kind of works through kind of several steps. So the first one is to initialize a population. So what was happening in the game just then is it was randomly generating a population of those vehicles, and within the kind of genome of those vehicles, using random numbers, the kind of is describing the shape of that car body, the diameter of the wheels, the weight of the wheels, etc. And you can imagine all of those kind of key fields that have been generated randomly, kind of forming the DNA of each individual in that kind of group of 20. So they've each got a kind of unique DNA describing all of those kind of key fields that we're interested in, and they've been randomly generated at this point in time. So we've got 20 randomly generated individuals. What we then do is we evaluate fitness. So exactly as we were looking at in the app just then, clearly we can directly measure fitness from that by how far down the track they managed to get. In our knapsack game, it was how many points did somebody manage to get, and that sort of thing. So we can just rank those highest to lowest, and understand where the fittest is and where the least fit is. Next thing we need to do is we need to kind of cut off some arbitrary point, the lowest scoring individuals, and we need to remove them from the gene pool. And this seems a bit harsh and needs to be kind of thought about really carefully when you're configuring your genetic algorithm. How many items how many individuals should you remove from the population each generation? Now, the reason it's important is if I remove too many individuals from the generation, there'll be certain kind of characteristics within there that didn't work out particularly well for that individual in that particular race. But actually, if passed on to an offspring and combined with some other kind of key attributes, could have actually kind of given birth to a really, really good racer. So clearly, if I'm culling the too many of the lower scoring items, I'm getting rid of some of those characteristics too early. But similarly, if I draw the line too low and only get rid of 1 or 2, I can only generate 1 or 2 new vehicles each generation, and therefore, it's going to take me a long time, a lot of generations, to make any progress towards finding the optimum solution. We then get to kind of reproduction. So having kind of culled off a few members of the population, we now need to crossbreed and cross-select some new offspring. So what happens here is generally speaking, the fittest individuals have the highest probability of reproducing, and it kind of works. The probability works its way down as you go down the list. two individuals come together, we get a crossover of their kind of DNA, of their individual solution, which is kind of random. So the offspring inherits a combination of genes from its parents, just like in real genetics. And then in some cases, and depending on what we set the mutation rate at, they might also inherit some sort of random mutation to their DNA, which again starts to introduce new kind of ideas, new concepts into that DNA, which may make them fitter, may make them worse. And what we do is we just keep going round and round that cycle, and each generation we're breeding more individuals. Hopefully those individuals are inheriting the good genes from their parents and inheriting fewer bad genes from elsewhere in the population. And so gradually we expect those individuals over multiple generations to get better and better. And yes, I do appreciate this diagram in the top right isn't particularly accurate, and I'm never quite sure why this guy at the front's doing a fist pump, but it's a good representation of the idea of kind of increasingly fitter solutions to the problem. Let's have a quick look if I can click on it. Wrong one. To get rid of this. See how our races are getting on. So we can kind of see. Let's fast forward to the next race. Start to see if we're getting any better races coming out. Looks very similar to where we were before, really. But if we leave this long enough, we can see that some of the population's starting to get much further down the track. They were before quite heavily concentrated around the start line, all dying off at the same time. This one here is still clearly managing to do much better. But maybe if we come back and give it a bit longer, we'll see some more. Here's a new one. So that's obviously inherited, some interesting genes from its parents and those sorts of things. So if we keep going back, we'll see this kind of continuing to get better. This game, by the way, really, really addictive. You can lose hours of your life. Right. Okay. So linear optimization then, pros and cons. So the pros, you can solve really, really complex problems with linear optimization, non-linear optimization algorithms. The real world problems are particularly thorny, and non-linear algorithms have some of the capabilities to really get under the skin of that, really find the best possible solution. The downside is, as you've seen, you've got to run them for a long time. You've got to run a lot of generations through them. They are computationally expensive. You also do need to know what you're doing when you're setting them up. There are a lot of hyperparameters around mutation rates and population sizes and other kind of key elements that you need to kind of keep track of and kind of set to try and make sure that you're getting the best possible outcome. Ultimately, with any massively nonlinear problem, you can never be entirely sure that you found the global optimum. Basically, what you're doing is it's the equivalent of setting someone down, in the Himalayas with a blindfold on. You're trying to find Mount Everest by constantly walking uphill. You can never be entirely sure that the hill, once you reach the top and you can't go in any direction without going downhill, you can never be entirely sure that you're standing on Everest. GAs and everything else get around that by having a large population that are all coming from the problem from lots and lots of different angles and lots of different spaces, but you can never be 100% sure that you've definitely found Everest. The only way you can start to get more and more sure is to run it a few times from different starting parameters and check that you always converge in the same place. Okay, so I've talked a lot there about linear optimization. I'm mindful of time, so I need to bring this to a close. But what about uncertainty? Because everything we've talked about now is about kind of solving the problem, find the optimum solution given what we've articulated. But again, the world is very rarely that simple. So in our jewelry theft game, we were looking at we had a 50 kilogram weight limit on our bag. And if we stick with 50 kilogram weight limit and we keep running the optimizer over and over again, we'll always get the same answer, which is our 118 score, and we'll always select these 6 items that are on the screen at the moment. But what if we didn't know that the exact limit of that bag was 50 kilograms? Because quite frankly, we're unlikely to know. We'd probably have to destructively test it, and then we can't use the bag anyway. So what if we assume that the actual limit of the bag is somewhere between 40 and 60 kilograms? What we can do is we can have a look across that uncertainty range. We can optimize all the different possibilities, and we can look at how often different items are selected based on the limit of the bag. And what we can see is a much more differentiated picture. So these 3 up here are still selected in 100% of all of the scenarios that we look at, across whether it's 40 kilogram limit or 60 kilogram limit. They are relatively insensitive to uncertainty around the weight limit of the bag in this particular scenario. We can also see that these items down here never get selected. It doesn't matter if it's a 40 kilogram limit or a 60 kilograms limit, they never get selected. So again, they are non-sensitive to the uncertainty around the limit of the bag. But these items here, all have a different range of time. So, from kind of, 75-ish% of the time, down to just sort of 5% or so of time when they're actually selected. And so therefore, actually, what the actual weight limit of the bag is does directly impact on whether or not these are the optimum things to select or not. Now, if the problem that we were trying to solve is relatively relatively symmetrical, i.e. the penalty that I pay for accidentally putting slightly too many items in my bag is about the same as the penalty I pay for accidentally putting slightly fewer things in the bag than I could have done, then we can kind of read off here that actually anything kind of much above kind of 50% would probably be the right things to do. So we'd probably take the first 6 items on this list as being most likely to be the right solution for us, because they exist in more than 50% of the futures that we've looked at. But in our jewelry theft problem, the problem was not symmetrical. So clearly, if I didn't choose an item that I could have fitted in my bag, then I lose the value, the potential value of that item. But if I chose to put something in the bag that exceeded the limit, then the bottom of the bag was going to fall out and I'd lose everything. So actually, I've got a lot more downside risk than I've got upside. And that makes a big difference in terms of when we start to look at actually what would be represent the optimum items to select given the uncertainty. It makes a big difference to what we choose. So actually, we end up choosing a different selection. The first 4 and the 6th item are the ones that we would choose, purely because we have an asymmetrical problem with not wanting to lose everything that's in the bag as we try to escape from the police. So let's assume now that we go a step further, and rather than just robbing one jewelry store, we're going to join a gang, and we're going to rob a whole number of jewelry stores that are all kind of they're franchises. They're all laid out the same. They all have basically the same items, and we all buy the same cheap swag bags because we're not wise enough to invest in stronger bags. So what we can then do is start to look at how does my kind of exposure to that uncertainty kind of change my decisions over time. So jewelry heist number 1, as we've just seen, I'll select a range of different things that kind of yield me about £99 worth of value, but mitigate my exposure to that downside risk, which is that my bag rips and I lose everything. Maybe on the same night, one of my compatriots robs a different jewelry store, and then that evening shows off and says actually he managed to get 44 kilograms in his bag and everything was fine. So I now know that the bag is capable of taking at least 44 kilograms, and now I can modify my approach, and I can select some different items in my next robbery. Maybe in my next robbery, we get back in the evening and somebody talks about the fact he got massively overexcited, put about 58 kilograms worth of items in his bag, and the bottom dropped out, and he lost absolutely everything. So again, now my understanding of the maximum limit has dropped. And as I kind of walk through kind of each robbery I undertake and each conversation I have with those other people, my uncertainty around the capacity of that bag is shrinking. And converging around a particular item. And what we can kind of see down here is my maximum kind of utility that I can achieve without taking any risk of downside loss is increasing over time. So what this allows me to do is to adapt my plan as I'm going around the uncertainty as I'm aware of it, and make sure that I'm always getting the maximum I can achieve from my robberies without taking too many risks. Okay, so let's bring this to a close. And so what does this mean in the real world? So obviously we've talked a lot about robbing jewelry stores and other bits and pieces. In the real world, the sort of work that we do with Arcadis Gen, we're working with companies that have whether it's buildings or railways or water utility companies with pipes and treatment stations, etc. But ultimately, conceptually, what we're trying to do is exactly the same thing. We're drawing on all of their data to kind of give us a really good understanding of the current run rate of defects and issues that they've got with their assets, and we're predicting how those are likely to change over time, how that's likely to impact on the organization's kind of key deliverables, key things that they're trying to achieve. And then we're using these sorts of optimization techniques and these optimization algorithms to really search through all the different solutions and all the different ways that we could respond to those future states, to really identify the best possible plans that we can implement so that they can maximize their utility, their whether it's efficiency, value for money, whatever that happens to be. Where that uncertainty exists, we can kind of fold that in. We can look at how that uncertainty affects exposure to different events, and we can allow an optimization that adapts and responds and to the changing understanding of the world. And that's particularly important where you're looking at things like long-term climate change and the impact on the plans that might have. Things such as building kind of large offshore wind generating facilities where you've got uncertainty around the yield, which will be based on the weather. You've got uncertainty around the future cost of electricity and those sorts of things, where that will all have to be kind of folded into your thinking over time as to what is the correct way, how many turbines should we build, where should we build them, how should we connect that in. And that's really where these algorithms start to really come into their own and enable us to really kind of explore those problems in some detail and walk away knowing that we have actually found mathematically the best solution to the problem given all of the uncertainty that we've got. Okay, so in conclusion, we've kind of looked at a number of different optimization techniques. We've concluded that if you're going to rob a series of jewelry stores, it's good to have decision theorists amongst your numbers because we can maximize the utility that you're going to achieve. But more importantly, we've kind of looked at the various pros and cons of different kind of algorithms that are available to us. We've looked at how they can be applied to the problems and used to maximize our utility. So I'm going to bring it to a close there. I think we've got a bit of time for Q&A, so I'll pass back.
Perfect. Thank you very much, Dan. That was really good session, actually. Thoroughly enjoyed hearing you present. And we've already had Andrew in the chat saying excellent, thank you. So if you have enjoyed that watching along at home, please do quickly jump in the chat just to say thanks to Dan. It's our virtual round of applause for him. So personally, I was absolutely devastated to miss out on knowing if I was a good jewelry store robber or not. Because depending on how the recruitment game goes, I may retrain in that area. But yeah, absolutely loads of comments coming through there. Joel Turner, Christopher Hadley, Thomas Oliver, Mark Petterson, Robert Sellers, Josh, Amir, Judith, T. Sue, Andrew Logan again. So mate, loads of people out there at home watching along and saying thanks for your time, Dan. So that's awesome. As Dan mentioned, we have got 10 minutes or so, and Dan has very kindly said that he will stick around for some questions. So we've already got quite a few in the Q&A, Dan. So if you want to open up the Q&A, I'll obviously read them out and go through them with you, but sometimes it's quite nice just to read along as we go. So we'll maybe take that first question there at the very top from Amir. It's had a few upvotes, so obviously a couple of people keen to know that answer. Are there any rules of thumb to check quickly linear versus a non-linear problem and what approach to take? Yeah,
absolutely. So the critical thing is to try and visualize how that utility function is operating. So in our jewelry theft kind of concept, we know that the decisions that we make are relatively independent, i.e. the value of a set of earrings is not changed by the fact that I've also stolen some rings or a necklace or something like that. They are, the decisions I make are independent from that perspective. We also know that if we had no constraints, then the answer is to put everything in the bag, because that would always maximize your utility. So you always know that adding one more thing is driving the utility function up. So that starts to give you a feeling, the fact that the decisions are independent and the fact that the utility function will always increase the more things I add, starts to give you a feeling that you are looking at a linear problem. Where you'd start to recognize that it's a non-linear problem is, you know, that point at which you know, making one decision affects another decision. So a real world example that we come across quite often would be, you know, that, you know, let's say an electricity company, they've got to go into a compound to replace a transformer. Because they, in order to enter the compound, they have to, you know, take an outage, they have to shut down the substation and those sorts of things. They have to get people to site and all these sorts of things. So all of that cost is sunk at the point at which they go into that compound. Now, if the switch gear or whatever else that's next to the transformer is also likely to need to be intervened in the next few years, it's all of a sudden cheaper to do it now than it would be in a few years' time, because people are already there. And you've already taken the outage, you've already incurred all that cost. So now we start to see that actually those decisions are no longer completely independent. I'm starting to see that there's some connection between them that might change my decision. And that's a warning sign that we're starting to get into non-linear territory.
Perfect. Yeah, another great example. It's really nice when you can link it back to real world examples like that, Dan. So thank you for that. We'll jump to the next question down. Sorry, I'll just move that one out of the way. Jump to the next question down there from Hamad. Hamad's been really good actually attending quite a lot of these sessions, and I think it's more of a generic question from him, just in terms of some of your thinking around creating the game to understand the data science concepts. I guess you've perhaps done this with other clients previously. Does it help to explain the concepts? Is that why you've created it?
It does, yeah. I mean, yeah, again, with the sorts of customers that we work with, they're not data scientists and that's the thing, and you're actually generally challenging the status quo. So you're going into an organization and you have the unfortunate position of having to say, you know, I'm sure you're all very clever, you already know, you know, how your assets work and that sort of thing, but your decisions aren't good enough. You're not making the right decisions, and you could make better decisions. And this kind of magical algorithm is able to do that. And that's a very difficult concept, you know, for people to take on board. You know, that idea that, you know, a computer can do this better. The Beat the Optimizer game is kind of a response to that, because it gives you something that you can actually, you know, interact with and understand a little bit about, well, why is that the case? Why is it that, you know, that just listing everything in priority order and choosing the top few and that sort of thing, why is that not the best? Well, actually, you know, under certain circumstances it's, you know, it's not, and actually under most circumstances it's not. And so it just gives you a kind of, again, tangible way of communicating that point to end users.
Perfect. Thanks very much, Dan. Next question there is from Daniel Jones. Daniel asks, using these optimization algorithms requires a good utility function. How do you identify a good value function when doing this in the real world?
Yeah, so typically, I mean, every organization we deal with has have things that are important to them, have measures, KPIs, you know, that they are tracking, measuring, they are themselves measured against, and those sorts of things. So they represent the critical things that you're looking for in the utility function, in terms of that's the thing that you want to maximize or minimize. So then it's purely then a case of being able to tie those back to the decisions that you're making, and understanding every single decision that you can make, how it you know, positively or negatively impacts on those items. And that can be anything from, you know, again, you know, just engineering knowledge about, you know, the impact of those. More commonly, kind of, you know, historical analysis on, you know, similar decisions, similar changes that have happened in the past, and how that's impacted on key metrics and other bits and pieces. The critical thing about the utility function is it's got to mean something to someone. It's got to be a tangible thing, and you've got to agree that having the maximum or minimum of that is therefore represents the best possible plan. As soon as there's any ambiguity around that, then anything that you're doing with an optimization function is probably moot.
Perfect. Thanks very much, Dan. Next question there from John. John's asking, do you know of any R packages for genetic algorithms?
Yeah, there are actually yeah, a few. There is one just called GA, I believe. Yeah, but yeah, they are. You can find them quite often. I'd also recommend try your hand at making one. They're not that difficult to make, and you'll learn an awful lot more about how they work by trying to make one.
Perfect, thank you. And we'll go to the second question down there from Amir, and it's very similar but in Python. Could you please share some examples of GA libraries in Python? Is there any out there in Python that you know of?
Again, there will be quite a few. I don't think I could name any off the top of my head, because we mainly use R, but I'm happy to take that away and we can come back you know,
Perfect.
later.
Thank you very much. 3 questions left, and we've got about a minute, so we might not get there, but we may run over for a minute or two as well, Dan, if you have a minute or two extra. Question there again at the top from Amir. Could you please share some of your thoughts and experiences on derivative-free optimization methods such as particle swarm, evolutionary, etc.? Is that something that you've come across?
Yeah, a little bit. So really kind of pushed me there. I mean, evolutionary is kind of fairly similar to what we've been looking at. I mean, there are a lot of different non-linear approaches. You've got things like simulated annealing. You've got quite a few different approaches, and they've all got their pros and cons. They're all, unfortunately, any time that you're in kind of non-linear territory, there's always a computational price, and one of my former colleagues had a kind of rule of thumb that kind of said, well, if you start off, is it a linear problem, well then use a linear optimizer. Is it a non-linear problem, then try and make it a linear problem and use a linear optimizer. The non-linears should be your last resort, because as soon as you get into that space, the problem you're trying to solve is really, really complicated, and you've got to really, really think about how to set that up. And it's very difficult to sometimes automate that, because they won't always respond well when some key factors change and other kind of key elements. But
perfect. Thanks, Dan. We'll go to that question there from Mark Petterson. Have you had any experience with SAT solvers or other constraint-based tools?
Not direct, no. I mean, some of my team probably have, but I've not had any direct experience of them.
Perfect, thanks very much. Then we'll just quickly touch on this one from Katie, and then kind of wrap things up a little bit and go from there. Katie is asking, please can you leave the game open to try again with some of my colleagues? Is that something that you'd be happy to leave open?
Yeah, I'm sure we can leave that open for a little bit,
there you go, Katie.
We'll have a look in the background as to why it wasn't working for everyone as well.
Dan will be analysing your how good of a robber you are, Katie. So yeah, putting a fake name. We'll start to draw things to a bit of a close now. I will just quickly get back into the chat here. Awesome talk. I really enjoyed it. Thank you from Laura. Kitash, thank you. Katie Gubler, really great examples. Chitty, Francis, Selcat, Sarah, Adam McGough, Mark, John, Seikat, Akish, all saying thank you very much for giving up your time. So just as we're bringing things to a close, I'd definitely love to reiterate that from our side of things. As mentioned at the start, Arcadis Gen have been great partners for the Data Science Festival, really supportive of the community, and also very keen to share some of the good stuff that they work on as a business. So thank you very much, Dan. I really enjoyed the talk, and hopefully actually we've got quite a few plans for later in the year, so perhaps we can loop back and get you on again at sometime down the line. But thank you all very much for joining. Thank you very much, Dan, and thanks again to Arcadis Gen.
Thank you for having me.
Perfect. See you soon, Dan. See you soon, everyone. Bye-bye.